I'm Dr. Harry Cliff. I'm a particle physicist at the University of Cambridge, and I'm also a populariser of science and science writer. Welcome to my exp. I work on a machine called the Large Hadron Collider, and this is the largest particle collider in the world. And essentially what it does is really simple and brutal. It takes particles called protons, smashes them into each other with lots of energy. And this is there's a long tradition in particle physics of these sorts of experiments where you smash particles into each other. And the reason for doing this is maybe not quite what you would expect. There's this term that's used to describe particle colliders as atom smashers, which kind of gives the idea that we're using these machines to smash atoms apart to see what's inside them. But that actually isn't really what colliders are for, because we know what's inside atoms. We discovered that in the 20th century pretty well. So actually what colliders like the Large Hadron Collider are matter factories. So the reason you accelerate these particles to very high speeds is that when they have very high speeds, they carry huge amounts of energy. And when you collide them, that kinetic energy is converted into new matter. So you're actually making matter, making new particles from energy. So in one of these collisions, when say two protons collide, you're not seeing the inside of the protons coming out. Well, you partly are seeing that, but a lot of the particles that you see coming out of that collision are actually particles that didn't exist before the collision. They were created in the collision. So this is a way of studying the sorts of objects that can exist in the universe. And in particular, when you get to really high energies, you're probing energy densities and temperatures and conditions that haven't existed in the universe in any large amounts since about a trillionth of a second after the Big Bang. So you're really probing the kinds of things that were going on in the very first moments of the universe. And this is why these experiments are so interesting. So 4th of July 2012 was a really exciting day if you're a particle physicist. There was this big seminar called at CERN, which maybe if you're not a scientist doesn't sound very interesting, but this was a really special event. And it was the announcement by two of the big experiments on the Large Hadron Collider, two experiments called ATLAS and CMS, which are huge particle detectors, each with about 3,000 physicists working on them. They sat on opposite sides of this 27-kilometer ring. And they both announced that they had seen conclusive evidence of the existence for a new fundamental particle that had been hypothesized almost 50 years earlier in the mid-1960s. And this is a particle called the Higgs boson. So the Higgs was sort of, for many years, the holy grail of particle physics. It was the thing that everyone had been looking for since it was predicted, more or less, in the 1960s. And the Higgs really plays an absolutely crucial role in our understanding of particle physics. In a sense, it's sort of like the keystone in an arch, where the arch is the standard model of particle physics, our best description of the universe. And the Higgs sits right at the center of that. And its basic role, it's connected to why the elementary particles in the universe possess mass. The idea that Peter Higgs and actually several other theorists came up with in the mid-60s was that mass arises because particles like electrons and quarks interact with a quantum field. So this is an invisible cosmic energy field that fills the whole of the universe. And when particles like electrons or quarks move through this field, the field sort of imbues the property of mass into these particles. This idea is written in a sort of mathematical language, and it was proposed to solve a particular type of theoretical problem with our understanding of particle physics in the 1960s. But the problem was that, okay, you invent this new invisible field, but how do you know it's there? Well, the way you know it's there is if you can hit this field hard enough, this invisible field, then you can make it resonate, you can make it ripple, and that ripple shows up as a new particle called the Higgs boson. So The reason the Higgs boson is really important and interesting is because its existence demonstrates that the associated field is also there, something called the Higgs field. And it's the Higgs field that gives mass to the quarks, the electrons that make up our bodies. And if it wasn't there, well, atoms couldn't form because electrons and quarks would never bind together to form stable atoms. So it plays an absolutely crucial role in shaping all of the ingredients of our universe and making our universe somewhere where atoms and therefore things made of atoms like stars and people can exist. The Higgs boson was so important to our understanding of particle physics that it was rather hyperbolically referred to as the God particle. So this, I think, originated in a book by Leon Lederman, who's a very eminent particle physicist. And his story is that his publisher wanted to call it the God particle because he knew it would sell way more copies. I think Lederman joked that it should have been known as the Goddamn particle because it was so hard to find. So this association, this name, the God particle, most physicists really don't like it because the Higgs boson has nothing to do with divinity or God or anything else like that. But it is, on the other hand, an incredibly important ingredient of our universe and one that's central to our understanding of particle physics. And not just that, actually, but it's also connected to some of the really big outstanding mysteries, so questions that we do not understand about the basic building blocks of the universe. So it plays an absolutely crucial role. It's very, very important, but I wouldn't use the term God particle.